Alright, so next moved into another form of trigonometric substitution. So now we're looking at integration by tangent half angle substitution. So formerly we've looked at examples where we've let t be equal to tan x, but now we're going to look at the substitution where we let t be equal to tan x over 2. So this is basically another form of trigonometric substitution. So we're going to let t be equal to tan x in these cases. So when do these work? So the full method, a substitution for the values of dx, sine x, cos x, tan x, cosec x, sec x, cot x. So the derivative of this equation 1 is, so let's look at that equation 1. So we can see that if we differentiate this, dt dx should actually be equal to a half sec squared x over 2. But remember, sec squared x over 2 is equal to 1 plus tan squared x over 2. So when you put that back in, this is what we'll actually have. Now if we could remember that t is representing tan x over 2, so we're going to put that back in. So we'll have dt being equal to a half into 1 plus t squared. So this is basically, so dx should actually be equal to 2 dt over 1 plus t squared, of which in this case that t is representing tan x over 2. So furthermore, to derive the substitution for other identities, for example, if we've said t is equal to tan x over 2, that means that tan x over 2 is the same as t over 1, of which now we can illustrate this on a right angle triangle as this. So the angle is x over 2, so that means the opposite is t and the adjacent is 1. So from Pythagoras theorem, a squared plus b squared being equal to c squared, we can actually see that we can actually find that the hypotenuse is going to be equal to root of 1 plus t squared, of which the t is representing tan x over 2. So if we already know that the half identity for sine x is this, so this is what we already know, that sine x is equal to 2 sine x over 2 cos x over 2 from trigonometry. And that for cos x is cos x being equal to cos squared x over 2 minus sine squared x over 2. So the substitution for sine x is sine x being equal to 2 sine x over 2 cos x over 2 should actually be equal to 2 into t over root of 1 plus t squared and 1 over root of 1 plus t squared. And that shall be just because when we look here, we can clearly see that sine x over 2, which represents opposite over hypotenuse, is going to be equal to t over root of 1 plus t squared. So place that where we have sine x over 2. Then where we have cos x over 2, that represents adjacent over hypotenuse, because that's what cos x over 2 represents. So that's why we substitute it right there. And basically when you combine those, we'll have, so actually when you multiply these two brackets, multiply everything here, and you will end up with sine x being equal to 2t over 1 plus t squared. So that will be the expression for sine x. So the substitution for cos x is, now we have to derive that. So remember that cos x from trigonometry is cos squared x over 2 minus sine squared x over 2. So when you substitute the values in, so we'll have this squared and that squared. Then when we square those brackets, we'll have 1 over 1 plus t squared minus t squared over 1 plus t squared. So when we solve this together, we can actually see that the denominators are the same, so we can combine them, and we'll have cos x being equal to 1 minus t squared over 1 plus t squared. And that's going to be the equation 4. So by using equations 4 and 3 and 4, we can actually find the other substitutions. So tan x, which is usually sine x over cos x, shall simply be that divided by that, of which we shall end with 2t over 1 minus t squared. And cot x, which is cos x over sine x, shall actually be equal to that divided by that, which shall actually be to 1 minus t squared over 2t. And then cosec x, which is 1 over sine x, shall actually be equal to the inverse of this, which is actually going to be equal to 1 plus t squared over 2t. And then finally sec x, which is 1 over cos x, shall actually now be equal to the inverse of cos x, which shall be 1 plus t squared over 1 minus t squared. So now that we know those, you can actually use these in examples. So imagine you're given the question, evaluate the integral of 1 over 2 plus cos x dx. So when you look at this example, you cannot directly just use any other method. So use substitution will not work. So basically most of the solutions that we know cannot work. So in this case, we can only use the substitution t is equal to tan x, or weierstrass substitution. So this is what we have. So by tangent half angle substitution, we remember that we've said that dx is equal to 2 dt over 1 plus t squared, because the derivative, that's what we get when we differentiate tan x over t be equal to tan x over 2. And then we've seen that cos x is equal to 1 minus t squared over 1 plus t squared. And that's what we need for this example. So where t is tan x over 2. So when you plug these in and substitute them, so where we have cos x, we've substituted it with that, and then where the dx, we actually substitute it with that. So now I can see that we'll have 2 over 1 plus t squared at the numerator, and we shall leave the t where it is. So now this is what we end up having. So here we find the LCM, and the LCM shall be equal to 1 plus t squared, and then this divided by 1 shall be equal to 1 plus t squared times 2 up there. So this is what we end up having. So basically next I can multiply this in and open brackets, and I'll have 2 plus 2t squared plus 1 minus t squared, which will actually be equal, give me an answer of 3 plus t squared. So next I can say that this and this cancel, and I'll be left with the integral of 2 dt over 3 plus t squared. And then I can actually pull out the 2, and I'll be left with the integral of 1 over 3 plus t squared dt. So next I can see that I can actually factorize out a 3. So when I factorize out a 3, I'll have 3 into 1 plus t squared over 3. Now basically the squared of root of 3 is what gives us a 3. So I can combine these up and square them, because I now want to solve them. I want to use the knowledge of inverse trigonometric functions. So now I can pull out this 3, and I have 2 over 3 into the integral of this. So I'll be left with 1 over 1 plus t over root of 3 squared. So now basically the next step is I can let u to actually represent t over root of 3, of which du dt shall actually be equal to 1 over root of 3. So when I make dt the subject, dt shall actually be equal to root of 3 du. So I can plug that back in, and I'll end up having this. So I now have 2 over 3 into the integral of root of 3 du over 1 plus u squared. So I can again pull out that root of 3, and I'll be left with 1 over 1 plus u squared. So remember the knowledge from inverse trigonometric functions, the actually tan inverse. Remember that when we differentiate tan inverse of x, we get 1 over 1 plus x squared. So that basically means that right here, this was, if we are getting the antiderivative, so that means we're actually going back to the tan inverse. So we basically going to have tan inverse of u. So we have 2 root 3 over 3 tan inverse of u plus c. So this is what we end up having. But remember that this and this can be combined, because 3 to the power a half minus this, so you're gonna have it as a half minus 1. So combine their powers and subtract them, and then we'll have 2 to the power 3 to the power negative 2 times 3 to the power negative a half tan inverse of u, of which we can take that back down, and we'll have 2 over root of 3 tan inverse of u plus c. But remember that u is t over root of 3, so therefore we'll have 2 over root of 3 tan inverse of t over root of 3 plus c. But remember t is equal to tan x over 2, so therefore our final answer shall be 2 over root of 3 tan inverse of bracket 1 over root of 3 tan x over 2 plus c, and that is our answer. So the next question is a question from UNEB 1993, and this was question 7 part 2. So we have the integral of 1 over 3 minus 2 cos x dx. So we're going to use tangent half angle substitution. So remember dx is 2 dt over 1 plus t squared, and then cos x, as you remember, is 1 minus t squared over 1 plus t squared, where t is equal to tan x over 2. So we're going to substitute those in, and this is what we end up having. So you can say that this actually goes to the numerator, and this is what we'll have. So when you find the LCM, we'll have 3 times 1 plus t squared minus 2 into 1 minus t squared over that. And then when I open those brackets, I can say that we'll have 3 plus 3t squared minus 2. Then this sign will change, minus 2 plus 2t squared. So next, this is what I'll have. So 3 minus 2 is 1, and then 3t squared plus 2t squared is 5t squared. So next I can see that this and this will cancel, and I will be left with 2 dt over 1 plus 5t squared, of which I can pull out a 2, and I'll have 2 into the integral of dt over 1 plus 5t squared. But remember that this can actually be, so we can actually use tan trigonometric substitution. So this is the same as root of 5t, and then combine them, and we have it as a squared. So basically it's like that. So now we're going to let u to actually be equal to root of 5t. So du dt should actually be equal to root of 5, of which dt should actually be equal to du over root of 5. That's what happens when you make dt the subject. And then put that back in and we'll have this. So we can actually see that we can pull out a 1 over root of 5, and we'll have outside we'll have 2 over root of 5 times the integral of 1 over 1 plus u squared du, of which we know that from inverse trigonometric functions that this actually represents tan inverse of u plus c. So we have 2 over root of 5 tan inverse of u plus c. But remember that u is actually root of 5 times t. So now place that back in and we have 2 over root of 5 tan inverse of root of 5 times t plus c. But remember t is tan x over 2, so therefore our answer is 2 over root of 5 tan inverse into bracket root of 5 times tan x over 2 plus c, and that is the answer. So question number 3 is a question from UNEB 2007, and this was question 13b. So being told to use the substitution t is equal to tan x over 2 to evaluate the integral. So we actually have limits. So the upper limit is pi over 2 and the lower limit is 0 over, and then we have 1 over 1 plus sine x plus cos x dx. So by tangent half angle substitution, remember that dx is 2 over 1 plus t squared dt, and then cos x is actually 1 minus t squared over 1 plus t squared. And also remember now we need what sine x is. Sine x is 2t over 1 plus t squared, where t is equal to tan x over 2. So substitute those back in and this is what you end up having. So I can see that this value goes to the numerator, then this is what I will have. So basically I can solve these values here and find the LCM. So the LCM is 1 plus t squared, so I'll combine them, and then I'll have 1 plus t squared plus 2t plus 1 minus t squared, like that. So we're going to simplify that, and then when you open brackets we shall have 1 plus t squared plus 2t plus 1 minus t squared. So you can see that this and this cancel, then we'll be left with 2 dt over 1 plus t squared over 2 plus 2t, because 1 plus 1 is 2 over 1 plus t squared. So next I can see that this and this cancel, and I will be left with the integral of 2 over 2 plus 2t. But I can also see that the 2's can cancel, because I can factorize out a 2 at the denominator, and I will be left with the integral of 1 over 1 plus t. So now this case can actually be solved using u substitution. And then when I use u substitution, what I'll get is, so I'll use the u substitution where I'll let u be equal to 1 plus t, of which when I solve that I'll get ln 1 plus t. And then this will be it. And then therefore remember the limits are pi over 2 and 0. But remember we have to first substitute for t. Remember t is equal to tan x over 2. So plug that in and we'll have ln 1 plus tan x over 2 with those limits. So now we can plug in the limits and then subtract them. So we now have the group where we've plugged in the upper limit pi over 2, and then the group where we've plugged in the lower limit 0. So basically here we have 0 over 2, of which 0 over 2 is 0, and then pi 2 divided by 2 is going to be equal to pi over 4. So now basically, so therefore here tan of pi over 4 is the same as tan of 45 degrees, which is actually equal to 1. So we have ln 1 plus 1 minus ln 1. Now 1 plus 1 here is 2. But remember that ln of 1 is 0, so we're left with only ln of 2. So our final answer should actually be equal to ln of 2, and that is what they wanted. Alright, so I have an exercise for you. These are numbers that you can try out and get better at trigonometric substitution, where you let t be equal to tan x over 2. So there are quite some examples, but the answers are basically on the right hand side for you to compare. So I encourage you to try this out, and then I believe that after you've done them, you'll actually have a better understanding of this section. Thank you so much for watching. Thank you so much for watching this video. I hope the video really helped you. If it did, feel free to tell me below in the comments. I'll make sure to get time to read through your comments and to reply to you. And also, if you're new to this channel, I encourage you to join the community by subscribing. And then make sure to hit the notification bell so that you get updated every single time I upload a new video. Again, my name is Emmanuel Olega. Thank you so much for watching. See you in my next video.